Welcome back. So in the last topic we were discussing about the to find the strain that is change in length for a circular bar and a rectangular bar we have discussed. So next we are going to discuss about the composite bar, or we call it as a compound or composite bar. So this compound or composite bar will be having two bars of a different materials. Yes. The composite materials is nothing but having a more than two different materials what we mix it together or with having a separate materials, that what we call as a composite bar. So now in this we are going to discuss about the composite bars. So a composite bar will be having made up of two different materials, that is the both the materials will be rigidly fixed together, so that in the both the two different bars strains will be together under the external load. So when we are discussing about the components with having a two different materials bars which is rigidly fixed under the external load, as the strains in the two bars will be same because both the materials will be different, but the at the under external load condition the strain in the two bars will be are same. The stress will be stresses what will be there in the two bars will be different and depending upon the modulus of the elasticity of that particular material. See, no need to confuse here. In the both the bars the strain will be same, but the stresses will be different on the bars with respect to the modulus of elasticity of that particular material. So in this what happens, a stiffer or a strengthening bar will have a major part of the external load. When having both the bars rigidly fixed together for an external load, but even though depends upon the material which the stiffer bar will be having, so that bar will take in a major part of the external. Whenever we are applying a load on that, automatically the major part of that external load will takes place here. So next when coming to the in a composite system, the two bars of different materials may act as suspenders in the third rigid bar subject to the loading. As the length change in the length of the bars, both the bars is the same. So the different stresses are produced in the two bars because of the modulus of elasticity of that particular material. So now stresses in a composite bar. First we are going to see the diagram where you can able to see this. Let us consider a composite bar consisting of a solid bar of diameter small d. So solid bar, what this portion what we call we have mentioned here, you can able to see that portion what we call as a smaller diameter, solid diameter, where it is indicated with a small d. Smaller d, and completely encased in a hollow tube of outer diameter, that is capital D, and inner diameter, that is the solid diameter, is considered as small d, subjected to a tensile force. So we are not acting any compressive, so we can able to consider the tensile force where P, you can able to see the both the ends P, that is the tensile force, and you can able to see the length. So once the load, the tensile load applies, where you can able to see the difference, that is what we call as a change in length. So now we need to identify the change in length. What is the equation we need to identify to find out the change in length? That is in the stresses in a composite bar, right? So this hollow with the lines we can able to see the hollow, and this we can able to see the small d with the solid diameter. So now let the extension of a composite bar of length L. So where you can able to see this. So the extension, let the extension of composite bar L, that is length L to the change in length L to be change DL. DL is the delta L is nothing but a change in length. Let ES and EH be the modulus of elasticity. ES is nothing but a modulus elasticity of solid bar, and EH is the modulus of elasticity of hollow tube or hollow tube, solid bar and hollow tube respectively. Next, let SS and SH be the stresses. So S is nothing but a solid bar where we have a stress in the solid bar and stress in the hollow tube developed in the solid bar and hollow tube respectively. Since the change in length of the solid bar, see whenever the load takes place, so L becomes change in length. So since the change in length of solid bar is equal to the change in length of hollow tube. So whenever the length in the solid bar will takes place, so similar changes in or it will be equal to the hollow tube. So now based on this condition, we can establish the relation between the stresses in solid bar and hollow tube as shown below. So based on these conditions, so since the change in length of solid bar is equal to change in length of hollow tube, so we can establish the relation between the stresses in solid bar and hollow tube as shown in below. That is, as shown below is nothing but a stress in solid bar, that is into the length will be divided by modulus of elasticity in the solid bar will be equal to stress in hollow tube into length divided by modulus of elasticity of hollow tube, or we can able to directly by equating this you can write stress in solid, that is sigma h by Es into Eh, or you can able to write this equation only. So this shows the established relation between the stresses in solid bar and hollow tube. So that equation we can rewrite, that is sigma s, that is solid bar into length divided by modulus of elasticity into the solid bar will be equal to this equation. Now coming to now by using this area of cross sectional of, because we have in both the different bars. So in the earlier we used to have one rectangular cross section or circular cross section of only one material. So now here, so at that condition we used to find out only the area of that, whether it might be rectangular or whether it might be a circular. But in this case what happens, here having one is solid bar and one is we have a hollow tube. So each hollow tube will be having a different cross sectional area, and solid bar also will be having a different cross sectional area. So in this condition we need to find out both the area of cross sectional bar for both the hollow tube and solid bar. So to find out the cross sectional area of hollow tube, that is A, area of hollow tube into hollow tube, that is H indicates pi into capital D square, that is larger end square minus smaller end, divided by 4. So similarly for the area of cross sectional of solid bar, that is A into S will be equal to pi into D square by 4. So area is, that is D is nothing but the diameter of the solid bar, where the hollow tube is nothing but the capital D is nothing but an outer part of the hollow tube, and the small d is nothing but an inner part of the hollow tube. So by combining that we can able to identify the area of cross sectional. Next, area of cross sectional of solid bar is, that is pi by 4 into D square, that is D is nothing but a diameter of the solid bar. Now load carried by hollow tube, that is load we can able to identify the notation either P or H. So load carried by the hollow tube is stress of hollow tube into the area of hollow tube, that is load carried by solid bar is nothing but load of solid bar will be equal to stress of solid bar into area of solid bar. But P is nothing but load. So but P will be equal to PS, that is load of the solid bar plus load of hollow tube will be equal to stress of solid bar into area of solid bar plus stress of hollow tube into the area of hollow tube. So now the load will become this equation. Now by taking stresses out there, that is sigma is nothing but stress in the solid bar will be equal to sigma h. Sigma h is nothing but stress in the hollow tube into EES is nothing but modulus of elasticity of solid bar divided by modulus of elasticity of hollow tube. So the following equation can be written rearranging, or you can rewrite this equation, that is load P will be equal to sigma h. Sigma h is nothing but stress of hollow tube into elasticity of solid bar divided by elasticity of hollow tube into the area of cross section plus stress of hollow tube into area of hollow tube will be equal to stress of hollow tube plus A, that is A is nothing but area of hollow tube divided by modulus of elasticity of solid bar divided by modulus of elasticity of hollow tube into the cross sectional area of solid bar. So this is the equation to find out the compound or composite bars whenever we need to find out what is the load condition or what is the change in length. So by using this we can able to identify the equation, or by using this equation we can able to identify the load conditions in the prismatic bar with having two different materials.